Alright guys, let's get going with covalent bonds part D. So for this one, what we're going to do is we're going to look at two kind of weird covalent bonds, because there's a couple of ways that covalent bonds are just a little bit like non-standard, if you can believe nature has things that are non-standard. Then we're going to look at some things called polyatomic ions. Now we're going to look at these because these are really weird. They are ions that are made up of a bunch of atoms that are bonded covalently. So covalent bonds hold the ions together, but they're ions, so then they do covalent bonding. And then you get these compounds that have both ionic and covalent bonding like together, which is kind of trippy, so we're going to check that out. So without further ado, let us start with the very first weird kind of covalent bond, the coordinate covalent. Here we go. So the coordinate covalent bond is defined as a covalent bond where both electrons in the bond come from the same atom. Okay, that's the thing here. Is where it's not like before, like when we learned about covalent bonds, each atom brought one electron, two for a bond, right? Because you need two electrons to make a covalent bond, and normally each atom brings one. But once in a while, we have the situation where both atoms in the bond come from the same, both electrons in the bond come from the same atom. And here's how it works. And this is the example that is used most often because it is the ammonium ion, super fundamental to life and everything we know as far as life is concerned. It is like, thank goodness for this particular like thing. So anyway, here's how it works. This is ammonia. It is nitrogen covalently bonded to three hydrogens, right? So this hydrogen here has an X, and that hydrogen has an X, and that hydrogen has an X. Those are the electrons from the hydrogen, and they're just an X, just so we can see that they're different. And our nitrogen has 1, 2, 3, 4, 5 valence electrons. The dots, now the blue dots, those are from the nitrogen. So what happens is if you take ammonia, which is typically a gas, and you bubble it through water, what will often happen is you have this thing, a hydrogen ion. Now a hydrogen ion is pretty unique in that hydrogens only have one electron, like a hydrogen atom only have one electron. There's one proton in the nucleus, and there's like one electron floating around. So when it becomes a hydrogen ion, that one electron in the cloud it's gone. Like there are no electrons. So what this is effectively is a naked proton. It's a proton without any electrons whatsoever, just floating around in the water, and that's really, really unstable. It's naked. It wants to cover up just like you would if you got off the school bus and suddenly discovered you were naked. It's awkward. I don't know why people have those dreams, but there you go. So what happens is this hydrogen just floating around literally just bumps into those two electrons. And because it's more stable, boop, it makes a bond. And then this hydrogen ends up being right here. So that's the hydrogen. And the coordinate covalent bond is this one right here. These two right there, those are the two electrons that make the coordinate covalent bond. Now, the only reason that happens, right? Like, so the only reason this coordinate covalent bond happens is because this hydrogen doesn't have any valence electrons, doesn't have any electrons. So it's really quite an unstable situation. It's just a proton. There's a lot of positive pull. So when this proton or hydrogen ion comes and lands into like these two electrons, they just naturally form a bond. One just pops into the orbital for the hydrogen, the other one stays there for nitrogen, and bam, makes a bond. We know what happens because it does, and it's way more stable than it just like floating around like that. So there's that. And this is what this is the one example that you guys are going to be seeing and like required to like recognize as a coordinate covalent bond. It's this stuff right here called ammonium, and that's that. Oh wait, it's not that. One other thing, the way that you're going to see this written like all the time is because this is a hydrogen ion. This thing ends up having a +1 charge and is called an ammonium ion. Got it? Because the whole thing has a +1 charge, but these are covalent bonds, and you can tell because the electrons are just like placed in between the atoms that indicate sharing. And then you know that the whole thing is an ion because look, we have brackets. It's all walled off, and there's a charge up here. So that's how we know that it's going to be a polyatomic ion. Does that make sense? Hope so, because off we go to like the next like weird thing, and that's going to be network solid. Now, a network solid is a solid with covalent bonds linking all the atoms together in one big molecule, or what we call a macromolecule, right? The prefix macro meaning like large, right? Molecule meaning, molecule, and molecule means covalently bonded. Remember before, like we said, anytime we say the word molecule, covalent bonds, a perfect example of this is, well, diamonds. Diamonds are all carbon atoms linked together via covalent bonds into one giant structure. So this right here, this diamond, that is one molecule of diamond. There it is. Oh, PVC pipe. That's another good one. That's a solid. That's one giant molecule. It's a macromolecule. Doesn't matter how big or how small the piece of PVC pipe. It's one fat giant molecule. The most common example that's used for this though is diamond. That's why I put diamond there, because this is like the most common. Got it? Okay, so those are our two weird kind of covalent bonds. We have coordinate covalent bonds. Remember where you have both of these electrons right here come from the nitrogen, so they belong to the nitrogen, but it's used like to bond the nitrogen and the hydrogen together, right? And then we have a network solid, and that is a solid. And for all intents and purposes, this thing, it looks like it's ionic. It's all crystalline and solid and stuff, but it's not ionic. It is definitely a covalent bond. One really good way to tell the difference between a network solid and a covalent solid is that an ionic solid. The way to tell the difference between a network solid and an ionic solid, it's late in the day for me, is that network solids don't dissolve in water. If you took an ionic substance like a big, beautiful diamond cut piece of sugar, like a sugar crystal cut like a diamond, you throw it in water, it dissolves away. Diamond, not so much. So let's talk about covalent characteristics. Now it's going to be a little bit difficult here, right? Because we have regular covalent bonds, we have coordinate covalents, we have network solids, so there's a bunch of different kinds. Ionic substances, bam, super easy. There's one kind of ionic substance, that's ionic substances. Now covalent bonding can get weird. It has all different kinds of forms, so there's going to be more than one kind of category, right? So we're going to start with network solids because that's what we just talked about. And who doesn't like diamonds? I don't know. Network solids, they are very, very hard, and they are very, very brittle. So everybody says that diamonds are the hardest thing ever. Yes, diamonds are very hard. In other words, it's almost impossible to scratch it. But you hit a diamond with a hammer, and it's going to explode into a million little pieces because diamonds are very, very brittle. They're a covalent. They're a network solid, so they will just smash. They also have incredibly high melting points. I looked. Yeah, it's very, very high, and so they cannot conduct electricity, whether it's solid or it's melted. As I said earlier, it's because if it's a network solid, right? This is a covalently bonded. There are no ions present here whatsoever, and that's what you need in order to conduct electricity. You have to have ions. So they can't conduct electricity, like no matter what. They do not dissolve. But they also have geometric crystals, like beautiful, beautiful, beautiful. So for a network solid, this is very much like something that's ionic. High melting point, very much like something that's ionic. Geometric crystals, very much like something that's ionic. But it cannot conduct electricity, whether it's a solid or it's a melt, and it doesn't dissolve in water, so there's no conducting of electricity whatsoever because there are no ions whatsoever. And that's how we know that it's all covalent bond. There's other ways we know too, but that's like a really good tell. You guys get what I'm saying? Awesome. So let's go to our next covalently bonded thing, and that's what we're going to call molecular solids. These are like your standard covalently bonded things. The best and most common example of that is going to be our good friend and buddy of the ocean, plastic. A plastic bottle is like your quintessential covalently bonded substance. I mean, look at that, buddy. What an excellent example of a molecular solid. So here's the thing. It is soft. In other words, it's like squishy. You can like crumple a plastic bottle. It's you know, it's not like it doesn't shatter or anything, right? It also has, excuse me, a very low melting point. I looked up the melting point of table salt, and I think it's like 1,500 degrees Fahrenheit. So that's hot, dude. That's really, really hot. Plastic, a little bit lower than that to melt plastic, you know, like it doesn't take a whole lot of temperature to melt plastic. So that's what I mean by a low melting point, relatively speaking. Also, molecular solids cannot conduct electricity no matter what. This is why we wrap wires in plastic, right? Because the wire conducts the electricity, the plastic makes sure that the electricity stays in the metal and doesn't go flying out into like us. You know what I mean? It forms an electrolyte only. You know what? Don't copy that down. I don't really care about this. We're just going to skip that. I don't even know why I still have that. I want to get rid of it. Let's just pretend it wasn't there. Done. Okay, moving on. So here's the other thing, is that because ionic substances come basically in one form, solid, and covalent stuff comes in like solids, it also comes in liquids. Covalently bonded things also come as gases. Like they cover everything. Liquids, so covalently bonded substances that are liquids are immiscible in water. That is a vocab word. Only if non-polar. So the thing is, water is intensely polar. Water has very, very strong positive end and a very, very strong negative end. So water itself is very, very polar. However, molecular substances are immiscible. In other words, does not dissolve. That's what that word means. It means does not dissolve if they are nonpolar. So that goes for things like oil. Oil is very covalently bonded. Let's just stick with oil. Butter, fats, things like that. Those are all covalently bonded molecules that are nonpolar. It doesn't dissolve in water, which is crazy. However, other nonpolar things, other covalently bonded things, like alcohol, that's a very polar molecule also, and it does dissolve in water. That's why we can get something like alcohol to dissolve in water, because it is a polar molecule. So it dissolves in polar solvent if polar. That's like alcohol and dissolving in water. The clutch thing that we should all have like locked inside our head is like dissolves like. Polar things dissolve polar things, non-polar things dissolve non-polar things. Now we're going to spend a whole chapter, maybe half a chapter, talking about how things dissolve and determining what does and what doesn't. But for right now, what we need to know is that if it is polar, it will dissolve in water. If it is non-polar, it will not dissolve in water and can only dissolve in a polar in a non-polar solvent. So polar with polar, non-polar with non-polar. Is that good? I hope so. I feel like I'm like messing stuff up all over the place today. Well, today's a bit human, and I'll probably be the most human teacher that you'll ever have. Whew! All right. One more point I want to make about covalently bonded things is that they are not all created equal, just like our ionic things, right? So for things to be covalent, they have to be lower than 1.7. So let's go 1.6 all the way down to 0. Got it? So if we have something over here at 1.6, you know, it may make it a slightly geometric crystal, and it might be kind of brittle. But you come way over here at like an electronegativity of 0, that's where it's going to be very soft. It's going to bend super easy, and it's not going to, like, it will not be brittle whatsoever. Over here at 0, you're going to have like a relatively low melting point, like maybe even like below 0. Whereas if it's up here, excuse me, long day. If it's up here, if you have like an electronegativity difference of 1.6, maybe 1.5, man, maybe you have to go all the way up to like maybe 200 or 300 degrees to melt it. So you could have a huge range of melting points, and it's all relative, right? We're just sort of comparing. But covalently bonded things, again, there's sort of a range. Way over like towards the 0 end, this is where you get things that are like more covalent, right? So these are the like the lowest boiling points, the lowest melting points, the absolute zero conductivity. Whereas over here on this end, when you come way over here to like 1.6, 1.5, that's where maybe it might be actually a little bit brittle. Maybe, you know, maybe you've seen some plastics that can like shatter when they break. That's because the electronegativity differences are probably pretty great, you know, like that kind of thing. And the way that we tell is the difference in electronegativity. The smaller the difference in electronegativity, the greater the covalent characteristics. Oddly enough, just the opposite of ionic. Yeah? All right, so let's move on to this thing. These things, these polyatomic ions, let's break it down right over there. Poly means like many or more than one. Atomic, guys, if you don't know that this means atoms, I can't help you. And ions, that just means ions, right? So this means more than one atom making an ion. That's what polyatomic ions mean. And that's what they are. They are ions made of covalently bonded elements. And this is so important to have here. They are covalently bonded together. So the thing that holds them together to make, like, to keep all those poly atoms together is a covalent bond. However, the aggregate, the clump of them, has either gained or lost electrons, and so that it, like they have a charge, right? And there are like a bazillion different kinds of polyatomic ions, but we are only going to be worried about these right here. Wait, let me get my face out of the way. These right here on table E. These are the ones that these are the ones that we are going to be looking at. Those are the ones that you're going to be responsible for. Okay? So the entire year, I promise you, if there is a polyatomic ion, it will be right here on this on this table. Nowhere else. Okay? And now here's the thing. Something like this one. Remember the ammonium that we were just talking about the other day? Or let's look at the carbonate, right? Or the hydrogen carbonate, or the oxalates, or over here, the nitrate. So NO3 or C2O4, let's look at C2O4. This is one ion that has a charge of 2 minus, or minus 2, like whatever you want to look at it. And so when we look at it, even though there are 2 carbons, and yes, there are 4 oxygens, giving a grand total of 6 atoms, hence the polyatomic part of this ion, it is one ion. So all of these ions act as though they are one thing. Okay? It is one block of an ion. So this is how it actually acts. Do you guys understand what I'm saying? So when it's floating around in solution, it acts like it's one block that's a +2, but when we write it down, we want to see what it's made out of, and it is made of, whoa, I erased way too much there. It is made of C2O4. Are you guys picking up what I'm putting down there? I certainly hope so. But like I said, they are all going to be right here. There's no, like, these are the only ones. There are no other weird ones that we need to worry about. That is it. But also, one more thing that we need to do is to draw Lewis electron dot diagrams for these polyatomic ions. Now, these Lewis electron dot diagrams follow the exact same idea that we had before when we took 2 atoms and we put them together with covalent bonds. Remember, 1 electron from each, 2 electrons to make 1 bond. And you just keep doing it until they all have 8, except for hydrogen, because hydrogen's a freak. That's why it broke off and floats up top. It's a little bit weird. It's the only one that needs 2. And I think I said last time the most electronegative thing goes in the middle. I think I was wrong. Again, why wouldn't I be wrong? So we're going to put the least electronegative in the middle. And then for every -1 charge, we add an electron. For every plus charge, we take 1 away. It'll kind of make sense in just a minute just by doing it. And I think that's what I want to do. I want us to go through and draw Lewis electron dot diagrams for 1, 2, 3 polyatomic ions. So this one is called OH with a minus. What is that one called? Let's come up here. Oh, here it is. It's called hydroxide. So the hydroxide polyatomic ion. Here we go. First thing I'm going to do is I'm going to draw my 2 atoms with their valence electrons. So I'll have oxygen and has 6. 1, 2, 3, 4, 5, 6. Okay, so where are my unbonded? So I have an unbonded electron there. I have an unbonded electron there. All right, so I bet you I know where the hydrogens are going to want to go. It's because hydrogen looks like this, right? It's H with 1 electron. So where could I put 1 hydrogen on there to make it bond and be happy? That's kind of what I was thinking too. I'm going to put my hydrogen right here. So there's my hydrogen. And there you go. There's the bond. Yeah? Does that make sense? So that's all the atoms. I've got 1 oxygen, I've got 1 hydrogen, but don't forget I've got the minus charge. So where am I going to put the minus charge? Somewhere on there to make everybody happy. And hydrogen's got its 2 valence electrons. It's happy. It doesn't need 1. But oxygen's got 1, 2, 3, 4, 5, 6, 7. Only 7. It only has 7 valence electrons. So I'm going to put that last electron right there.
Presentation for supporting students with grief and loss.
So that's how we do the OH. Oh wait, I almost forgot one thing. The one thing we have to do is we're going to, just like before with ions, we're going to put it in a bracket and say -1. So that's how we do that one. Are you guys picking up what I'm putting down there? Again, you just put out all the atoms as you can, making 2 electrons for 1 bond, and then add 1 electron for a negative, take 1 away for a positive, and that's how we do. Let's move on to H3O. So for this one, I don't know about like which one goes in the middle. I know that there are 3 hydrogens and 1 oxygen. I'm going to bet that the oxygen's the one in the middle. So I'm just going to start with oxygen with 6. 1, 2, 3, 4, 5, 6. Now I can't forget here that I'm going to have to take 1 away to make this work. So I'm going to put that in my brain. I'm going to have to take 1 away to make them work. And I'm going to need 3 hydrogens. Well, I can see where I can put 2. So here's 1. There's 1 hydrogen. There's 2 hydrogens. Now I need to make a 3rd hydrogen. Where could I put a 3rd hydrogen? I can't right now. It doesn't work until it does. Because remember, I got to get rid of an electron. So I'm just going to get rid of that one because it'll be easy, and I'll put my hydrogen right there. Right?
Hello there again. One correction.
Hold on, guys. All right, I'm back. I had to pause for Miss Kelly because when she speaks, you listen. We all know that. Anyway, so getting back to this. So there we go. There's my 3 hydrogens. I had to take 1 out for it to work. And again, because it's an ion, you all know what we're going to be doing here, right? Put a big fat bracket on it and give it a plus. That way we know it is all 1 ion. And again, that bracket, we put that there to remind us it's acting as if it's one thing. Yes, it's made out of many little parts, but it's acting like it's one thing. Like we know, like this pen is 1 pen, but it's made out of many parts, right? Okay, that's not a big concept. Now this next one is looking a little spicy. NO2 with a minus charge. I don't care if it's spicy or not. I'm not scared. But since there's 1 nitrogen and there's 2 oxygens, I'm gonna bet that nitrogen is gonna be in the middle. I'm gonna guess. I don't really know. Let's just give it a shot. So here's nitrogen. It's got 1, 2, 3, 4, 5, and I'm gonna put 1 oxygen over here to the left, and I'm gonna go 1. I'm gonna draw it like this so that my single unpaired electrons are like kind of like close to each other, like facing them, so that I can see a little better. All right, so now I'm gonna just start. I'm gonna start making bonds, right? So I'm gonna take these 2. And I'm going to make them 1 bond. I love that. And now I'm going to take these 2. And I'm going to make them into a bond. Because that's what we do with covalent bonds, right? You take 1 electron from each, turn them into a bond. And this oxygen's done, right? 1, 2, 3, 4, 5, 6, 7, 8. That one's done. And so let's come over here to this dude. Let's put my other oxygen right here. And I'm going to give it the 6. It's 6, 1, 2, 3, 4, 5, 6, and I did it. Now remember, it's like this way versus this way. I drew the oxygen that way just because it's more convenient for me for like when it's on the paper, but it's the same thing. It doesn't matter if you draw it this way or that way, same thing. So let's go ahead and do this. I'm gonna make one more bond here. All right, now I'm at a bit of a crossroads here because this oxygen is done. 1, 2, 3, 4, 5, 6, 7, 8. It's super happy. Let's check out the nitrogen. 1, 2, 3, 4, 5, 6. Wait, sorry. Let me start over. 1, 2, 3, 4, 5, 6, 7, 8. That nitrogen is done. Like there's no more bonds anywhere, but just that poor oxygen. Oxygen is not happy. Look, 1, 2, 3, 4, 5, 6, 7. That is a very unhappy oxygen. What are we going to do? Oh, yeah, don't forget. Remember, there's the charge. Where could we put that one electron to make everybody happy? Where? Oh, you're right. Right there. And yes, you're right. Don't forget the brackets. Got it. Super easy. Awesome. Let's do more stuff. No more stuff? Actually, yes, a lot more stuff because right over there, more Lewis electron dot diagrams. Ooh, it's going to be spicy. But not really, because all you have to keep in mind is that you take one electron from each atom, make them into a bond. You do that until everybody has 8. Except hydrogen, who's weird and only gets 2. That's it. That's all there's to it. Yeah, we're going to be working on that one right over there together, and I look forward to seeing you guys soon. I hope you guys have an awesome day, because Lord knows I am. I'll see you soon, guys. Thanks for being awesome.